Hello students, in this video we'll prove the first algebraic Bianchi identity. So let's recall that the Riemann-Christoffel tensor is given by R, L, J, N, P is d by dxn of gamma L, Pj, Jp, minus d by dxp of gamma L, Nj, Jn. Again, the order doesn't matter, so I can flip them, right? And then plus gamma of NaL, gamma of A, Jp, minus gamma of PAL, gamma of A, J, N, like that. That's my Riemann-Christoffel tensor. And so the first Bianchi identity states the following. So this is Bianchi's identity for the algebraic version. There's also a differential version. It states that if I cyclically permute the bottom indices, I get 0 when I add them up. J, N, P plus R, L, N, P, J plus R, L, then P, J, N, like that. Okay? Great. So let's write these things out. So I've already written out the first thing over here. So this is my first, I've already written this first expression out. It's this expression right over here. So let's just keep that on the board because we have already written it out, right? Great. Now let's write the next two expressions, changing these things over here. So the question becomes is what is my RL, and then N, P, J, right? Let's figure out what this thing is going to be over here. So now what I'm doing over here is now my variables, now the role of J is being played by N, right? So everywhere there's a J in this formula, I'm going to replace it with N, and everywhere there's going to be a N, I'm going to replace it with a P, and everywhere there's going to be a P, I'm going to replace it with a J. Okay, great. So let's do it. So this is going to be d by dx what? N is the second slot over here. The second slot over here is a P, so that's a P derivative of gamma of L is always on top, and then over here I have a P, so playing the P is being played by what? P is being played by N, so it's going to be an N. And then I'm missing a what? Then I have a P, and then P over here is being played by J, right? Good. And then minus d by dx, what? P over here, P is being played by J, so that's going to be an xj, and then gamma of L, and then J over here is being played by N, and then N over here is being played by what? N over here is being played by P, like that. And then we have a plus gamma of N over here is being played by P, so P, A, L, gamma, A, and then I have a P and a J, so I'm missing an N and a J over here. So of course my J is being played by what? N, and my P is being played by J, so I have an N and a J over here. Then minus gamma of, what's my P? My P is my J over here, J, and then I have a what? Then I have an A, then I have an L, then I have a gamma of A, then I have a J, my J over here is N, and my N over here is P. Beautiful. So let's do the same trick over here. So I have R, L, dot. I'm going to cycle one more time, right? That's going to be a P, J, N. Okay? Let's use the same formula. It's because it's great practice. If you want to learn what the Riemann tensor is, these Bianchi identities are perfect because if you want to do them directly without any clever tricks like passing the GS and coordinates, this is the best way to do it. Okay, great. So what will this be? This is going to be d by dx what? d by dx. So let's figure out. So N over here is being played by J. So I have a J derivative over there. Good. And then I have a gamma L, and then what am I missing over here? So then I have a what? Then we're going to have a, let's see, I have a J and a P. The J and the P are the N and the P and the N. Minus d by dx what? d by dx P, but my P over here is being played by N, xn, gamma L. And of course, by symmetry over here has to be a tensor, so it has to be a P and a J, right? Let's make sure, right? I have a J and an N are a P and a J. P and a J, good. Plus gamma of my N over here is going to be a J, J, A, L, gamma A, and I'm missing an N and a P, right? So my J and P are my N and P, good. Minus gamma of what? My P over here is corresponding to an N, gamma of N, A, L, gamma of A, and then finally a what? I'm missing a P and a J. Let's make sure I have a J and an N, P and a J, perfect. Okay, so these are really what? I'm really just cycling the covariant indices. So here we just cycle the covariant indices and add. That's what the Bianchi identity is. Great. And now let's capture all these things over here. So now what will happen when I add these things together? So what will RL dot JNP plus RL of NPJ plus RL of what? Of dot PJN give us over here. Let's check it out over here. So let's look over here. Here's an XJ derivative over here. And then here's also an XJ derivative over here. And they have the same indices, right? One's negative, one's positive, so those cancel out. It doesn't matter if I have a P in N or an NPU because the Christoffel symbols are symmetric in the bottom indices. Good. Let's look at this X. Here's an XN derivative over here. This XN derivative over here can be matched with this XN derivative over here. That's a negative and that's a positive over here. Those two terms over there are the same and opposite, so those cancel out. And now let's look over here. What's next? What's next over here is this P derivative over here. This P derivative over here and this P derivative over here are going to cancel out by symmetry as well. So all the derivative terms have canceled out. And then what? And then what we get over here. So let's see, let's look at this gamma of NaL, right? So I have a gamma of NaL, and I have a gamma of NaL over here, equal and opposite. So those terms cancel out. Let's look at the PAL. That's a PAL, and that's a PAL. That one's negative, that one's positive over there. Those cancel out. And finally, I have a JAL and a negative JAL. Those cancel out. So all these things add up to 0. So that's the Bianchi identity, right? And now I can trace this over here. If I trace this over here, I can conclude that R of R, J, N, P plus R of R, N, P, J plus R of R, P, N, J is equal to 0 by tracing that equation over there. And that's the all-covariant Bianchi identity. Now there's one final sort of neat application of the Bianchi identity. And so here's one other proposition. It's rarely ever discussed, but it's a neat one to do. If I do gamma R, and then I trace on that first J index over there. And then I look at the NP. Let's write what this formula is going to be over here. This would be what? D by dx what? D by dx n. Then gamma L. And then my J is going to be an L over here. And then I put a P over here. Okay? And then I have a minus D by dx P. And then gamma L. And then again an L and then an N. L and an N. A plus gamma. And then I have an NaL gamma A what? A what? PJ, but that's going to be an L, right? So that's going to be an L. What do we have over here? So we have let's take a look over here. We have a JP, but my J is now L and P. And then minus gamma of PAL, gamma of A, and then NJ, which is going to be an LJ over here. So that's going to be, oops, excuse me, that's going to be an N. That's not a J. That's not a J. That's going to be an N, right? LN. Great. Now these two terms clearly cancel because you're tracing over the same things, right? You have an N and L in the indices, and you're tracing over L and tracing over A. If you could just change the L's to A's over here, those are the same traces. Now this thing over here is the what? This thing over here is the N derivative of the P derivative of the log of the square root of the determinant of the metric. This thing over here is the P derivative of the N derivative of the log of what? Of the square root of the metric. And mixed partial derivatives commute. So it doesn't matter if I do the P derivative first or the N derivative first, those things are the same, and that gives me 0. So in other words, this expression, you trace over the top index and the first bottom index over here, you get 0 for the Riemann-Christoffel tensor. So these are the first Bianchi identities, sometimes called the algebraic Bianchi identities. Thank you very much.